Hello, everyone, and welcome. One of the most satisfying things in all of math is finding a really beautiful shortcut for a problem that looks, well, completely impossible. And today, that's exactly what we're going to do.
Okay, just look at this thing. This is the kind of integral that makes even seasoned calculus students nervous. Why? Because all the usual methods just don't really work. It's a real beast. But what if I told you there was a secret way to solve it? Not with brute force, but with a clever little trick from a higher dimension. Stick with me because by the end of all this, you'll see exactly how to get the answer, and it's going to be surprisingly simple. All right, to find this shortcut, we have to change how we see things. So forget the good old-fashioned number line for a minute. We're going to a new place, the complex plane. This is where numbers have two parts, a real part and an imaginary part. And let me tell you, once you're in this new world, the rules for doing something like integration get a whole lot more flexible.
And this really gets to the heart of it. See, on a regular number line, if you want to integrate from point A to point B, there's only one path, right? A straight line. It's fixed. But in the complex plane, oh, you have options. You can go straight, you can take a big scenic arc, you can do a wild loop-the-loop, whatever you want. Each of these different paths is called a contour. And here's the crazy part. The path you choose can totally change your answer. So this is our new powerful tool, contour integration. And it's that very flexibility, the freedom to choose our own path, that we're going to use to find our shortcut. The whole game is about picking a path so cleverly that all the hard parts of the problem they just vanish. So how in the world do you pick the right path? Well, that leads us to the real superpower of this whole idea. It's a truly amazing piece of mathematical magic called the residue theorem. And believe me, it's going to turn that integral nightmare into something as easy as simple arithmetic. It all kicks off with this incredible insight from the mathematician Cauchy. Basically, he figured out that if you have a well-behaved function, one that's nice and smooth with no crazy jumps or breaks, what mathematicians call analytic, and you integrate it around any closed loop, the answer is always zero. Always. A big, fat nothing. But the really interesting stuff, the magic, happens at the points where the function is not well-behaved, the little trouble spots. And this is our shortcut. It's absolutely brilliant. The residue theorem tells us, forget about the long, complicated path of the integral. Just focus on those few little misbehaving points inside your loop, the spots where the function blows up to infinity. We call those spots poles. For each of those troublemaker poles, you calculate one special number, the residue, which is kind of like a measure of its strength. Then you just add up those numbers, multiply by 2 pi I, and you're done. That's it. An entire integral just boils down to finding a few points and doing some simple math. And there it is, the answer to that terrifying integral from the beginning, pi divided by 2 times the square root of 2. No pages of messy calculations, no pulling your hair out, just a clever path in a new dimension and a little bit of focus on the trouble spots. That right there is the power of this method. Okay, that was pretty cool. We've seen how this way of thinking can just demolish a tough integral. But this core idea of transforming a hard problem into a much easier one, it has even bigger fish to fry, especially when you're up against something like differential equations. So let me introduce you to the Laplace transform. I want you to think of it like a universal translator. It takes a really thorny differential equation, which is all about calculus and rates of change, and it translates it into a simple algebra problem. You solve the easy algebra, and then you just translate your answer back. I mean, for engineers working on circuits or control systems, this thing is an absolute game changer. This table right here, it's basically our translation dictionary. On the left, you've got your functions in their original calculus language, and on the right, you've got their translated forms in the new algebra language. All you have to do is look up the different parts of your equation, swap them out, solve the algebra, and you're almost home free. But there's that one last crucial step, right? Once you've got your answer in this nice, tidy algebra world, how do you get it back to the real world? How do you translate it back to what it means in reality? How do we do the inverse transform? Well, the official, by the book way, is with this beast of a formula, the Bromwich inversion formula. And what do you see sitting right there in the middle of it all? Yep, an integral sign. And just like that, our whole story comes full circle. The exact same idea we used to solve our first problem, contour integration, is the key to translating our answers back into the real world. Now, let's be real for a second. In practice, trying to solve that Bromwich integral by hand can be just as hard, if not harder, than the problem you started with. So, what do we actually do in the modern world? Well, we turn to our computers and find really clever ways to get an answer that's close enough.
This is the modern trade-off, really. On one hand, you have the analytical method, the Bromwich integral. It's theoretically perfect, it gives you the exact right answer. But a lot of the time, it's just impossible to actually do. On the other hand, you have numerical methods. They give you an approximation, sure, but they're incredibly fast, they're practical, and for almost any real-world purpose, they are way more than accurate enough.
And the absolute state-of-the-art for this stuff is something called the Abate-Witt framework. It's so clever. Instead of integrating along a whole path, it just samples the function at a few very specific, strategically chosen points in the complex plane. Then it combines those samples to build an incredibly accurate guess of the real answer. The whole trick is just figuring out where the best points are to sample from.
And that brings us right up to today, to the cutting edge. Methods like the CMES add another layer of smarts. It has a shifting parameter that actually adjusts the calculation as it goes, custom tailoring the approximation for the specific function you're trying to solve. This is a huge deal, especially for functions that die out really, really fast, which is where a lot of the older methods would just completely fall apart.
So all of this leaves us with a really fascinating question, don't you think? We started this journey with Cauchy's elegant, perfect 19th century logic, and we ended with the CMES method, a highly optimized computer algorithm that relies on pure number crunching power. So as our computers get more and more powerful, are we going to rely more on these smart approximations? And will the search for that one perfect answer become less of a practical necessity and more of a beautiful but maybe rarely used art form? What do you think the future of problem solving is going to look like? Definitely something to chew on. Thanks for joining me on this one.